Hello everyone, today we will learn the formulas for sine, cosine, and tangent of two angles and their differences. Firstly, we will start with the research topic of trigonometric identity transformation in this unit. What is trigonometric identity transformation? Let's take a look at our familiar induction formula 1, which reflects that the trigonometric function values are the same for the same final edge angle. By using the residual angle formula of this angle, we can deform the trigonometric function formula, thereby achieving the goal of simplifying evaluation and even proof. This kind of identity transformation of trigonometric functions using formulas is called trigonometric identity transformation. We first use the induction formula for simplification. Cosine half pi minus beta equals sine beta. Cosine pi minus beta equals negative cosine beta. Cosine negative beta is equal to cosine beta. Cosine alpha minus 3 second pi equals negative sine alpha. Subtracting 2k pi from cosine alpha equals cosine alpha. Let's focus on the common structural features of this set of questions. They are actually cosine structures with two angular differences. Some students may have doubts about the negative beta of cosine. I can see cosine negative beta as cosine 0 minus beta. It naturally also satisfies structural characteristics. Let's focus on the characteristics of the angle again. Half pi minus beta, 0 minus beta, alpha minus 3 second pi, alpha minus 2k pi. In fact, it is a special angle, the difference between 2k pi and any angle alpha or beta. We focus on the simplification results again, which are related to the sine or cosine values of any angle alpha or beta. We convert the special angles half pi, 0, 3 second pi, and 2k pi in this set of exercises into any angle alpha or beta. So these 5 questions will be unified as the problem of cosine alpha minus beta. We refer to it as the cosine of the difference angle. Let's think about which values may be related to the expansion formula of cosine alpha minus beta. By comparing the previous 5 equations, we found that the cosine alpha minus beta, the expansion may be related to the sine or cosine values of alpha or beta. So let's think about what knowledge we can use to explore the relationship between cosine alpha minus beta and the sine and cosine values of alpha and beta. This requires us to study past experiences. We recall the induction formula. When deriving the induction formula, we used the definition of trigonometric functions and the unit circle. Of course, for our induction formula 1, the final edge intersects the unit circle at point P, which rotates 2k pi around point O. Due to the special symmetry of the circle, this point remains on the circle and its position remains unchanged. So we obtained the same values of trigonometric functions with the same final edge. Derive the induction formula for comparison. So please use the definition of trigonometric functions to draw diagrams. Starting from the non-negative half-axis of the x-axis, take any two angles, alpha, beta, and their final edges, and intersect the unit circle at O1 and P1, respectively. So, we exclude the special case where the final edges of alpha and beta are the same. In fact, we can divide the drawing into the following 3 situations. The first type is any angle alpha, beta, and the angle within 0 to 2 pi that is the same as the terminal edge of alpha is greater than the angle within 0 to 2 pi that is the same as the terminal edge of beta. The second type is any angle alpha, beta, where the angle within 0 to 2 pi that is the same as the terminal edge of beta is greater than the angle within 0 to 2 pi that is the same as the terminal edge of alpha. Of course, there is also the type that everyone draws the most, where alpha and beta are both in the first quadrant, and the angle within 0 to 2 pi that is the same as the terminal edge of alpha is greater than the angle within 0 to 2 pi that is the same as the terminal edge of beta. Let's start with simplicity. Let angles alpha and beta be acute angles, and alpha be greater than beta. So as shown in the picture, point A is the intersection point between the terminal edge of beta and the unit circle. So the coordinates of point A are cosine beta and sine beta. P1 is the intersection point between the terminal edge of alpha and the unit, so its coordinates are cosine alpha and sine alpha. Remember everyone, we need to derive the expansion of cosine alpha minus beta, so we also need to find the points related to cosine alpha minus beta. How to find it? Of course, we still use the definition of trigonometric functions. Make an angle alpha minus beta starting from the non-negative half-axis of the x-axis. The intersection unit circle is at point P. At this point, the coordinates of point P are naturally cosine alpha minus beta and sine alpha minus beta. So, we now need to discover that there is an equal relationship between cosine alpha minus beta and the sine and cosine values of alpha and beta. We need to pay attention to the relationship between the trigonometric values of angles, so we naturally need to focus on angles. So we need to find the combination of the equivalence relationship related to alpha minus beta in the unit circle. So we know that OP is the angle alpha minus beta that we do. When alpha is greater than beta, then the angle O1 OP1 is still alpha minus beta. So we have found that the angle OP is equal to the angle O1 OP1, which is the difference between alpha and beta angles. We can draw many conclusions from the fact that these two central angles are equal. For example, we can obtain that arc AP is equal to arc A1P1. Of course, we also obtain the congruent relationship between triangle AOP and triangle O1OP1. We can obtain that two line segments AP are equal to O1P1, whether it is the arc or the congruent between triangles. So this is the main basis for us to derive the formula. For the sake of rigor in deduction, we now need to rigorously prove the equality of line segment A1P1 and AP. How can we prove it? We still need to pay attention to this picture. We focus on OP as the final edge of alpha minus beta. OP1 is the endpoint of alpha, so after rotating around O by a beta angle, OP naturally coincides with OP1. OA is the starting point. OA1 is the terminal edge of beta, so after OA rotates around O by beta, it naturally coincides with OA1. So this involves a fan-shaped rotation. So OP rotates around point O by a beta angle. Due to the rotational symmetry of a circle, if point AB on the circle rotates around O by any angle beta, it will still be on the circle, and point AP coincides with A1P1. Therefore, we obtain that arc AP is equal to arc A1P1. So the corresponding string AP is equal to a 1P1. Some people say that we have other methods here. The angle OP derived earlier is equal to the angle A1 OP1, which is alpha minus beta. Then we can know that triangle OP is equal to triangle A1 OP1. Naturally, it can also be concluded that the line segment AP is equal to a 1P1. We have now rigorously proven the equivalence of line segments, so the essence of the equivalence of line segments is an isometric problem. So next, we will introduce the formula for the distance between 2 points. If any 2 points A, x1, y1, b, x2, y2 in the plane are used to construct a right-angled triangle ACD with a b as the hypotenuse, then the length of AC is naturally the absolute value of y1 minus y2, and the length of BC is naturally the absolute value of x1 minus x2. So the square of a b is equal to bc plus AC, which is equal to the square of x1 minus x2 plus the square of y1 minus y2. So we have obtained the formula for the distance between 2 points, that is, AB is equal to the square of x1 minus x2 at the root plus the square of y1 minus y2. So let's use the distance formula between 2 points to represent the line segment AP and a 1P1, and then derive the formula for cosine alpha minus beta. Based on our previous drawing, we already know the coordinates of points P, AP1, and A1. So the square of AP is the square of cosine alpha minus beta minus 1 plus the square of sine minus beta. The square of a 1P1 is naturally the square of cosine alpha minus cosine beta plus the square of sine alpha minus beta. Due to the equality of the two lines, we obtain that their squares are also equal. In such an equation, we found 3 perfect square equations, and we expanded and organized them. Let's take a look at the equation on the left, where the sum of squares with the same angle appears. The cosine square alpha minus beta and the sine method alpha minus beta add up to 1. The equation on the right shows cosine square alpha, sine square alpha, and the sum is 1. The sum of cosine formula beta and sine formula beta is also 1. So the formula is organized as negative 2 times cosine alpha minus beta plus 2, equivalent to 2 minus 2 times cosine alpha and cosine beta minus 2 times sine alpha and sine beta. After a little sorting, we got it. When alpha and beta are acute angles and alpha is greater than beta, the specific condition is that cosine alpha minus beta equals cosine alpha, cosine beta plus sine alpha, and sine beta. Can alpha and beta meet my requirements in other situations? In the most special case, when the final edges of alpha and beta are the same, the left-hand side of the equation is transformed into cosine 2k pi, which has a value of 1. The right-hand side is cosine squared beta plus sine squared beta, which also has a value of 1. The left and right forms are equal, so the above equation naturally holds. Let's take a look at our situation again. Alpha, beta is any angle, and the angle within 0 to 2 pi that is the same as the terminal edge of alpha is greater than the angle that is the same as the terminal edge of beta. Because within the range of 0 to 2 pi, the angle equal to the terminal edge of alpha is greater than the angle equal to the terminal edge of beta, naturally alpha minus beta will form a counterclockwise rotation angle, that is angle OP. So we found that the angles AOP and A1OP1 are equal, which naturally leads to their corresponding chords AP and A1P1 being equal. Alpha, beta remains an arbitrary angle, and the angle within 0 to 2 pi that is the same as the terminal edge of beta is greater than the angle within 0 to 2 pi that is the same as the terminal edge of alpha. We still need to use the rotational symmetry of circles, so the fan-shaped OP rotates around O by a beta angle. At this point, it will coincide with A1 and P1 respectively, and naturally there is still a corresponding arc AP equal to arc O1 P1. It can also be obtained that a P is equal to single quotes A1 P1 single quotes dot SO naturally. The cosine formula for the difference angle can also be derived using the formula for the region between two points. Overall, for any angle alpha, beta, there is a line segment AP equals A1 P1. Therefore, we can naturally use the distance formula between 2 points to derive that cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. So, for any alpha beta, cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. We call it the cosine formula of the difference angle, abbreviated as such a symbol. So first of all, I want to emphasize, alpha, beta is an arbitrary angle. The left beta corner represents alpha minus beta, while the right corner represents alpha and beta. We focus on the right side of the expansion. Its form is multiplication of the same function and addition of symbols. We use the cosine formula of the difference angle to prove that one. Cosine half pi minus alpha equals sine alpha. Cosine pi minus alpha equals negative cosine alpha. In the question, we are required to use the cosine formula of the difference angle. Therefore, in the first question, we will naturally expand according to the requirements, paying attention to multiplication with the same name and addition of symbols. So, it is cosine half pi, cosine alpha plus sine half pi, sin alpha. Substitute the numerical value to prove that its value is sine alpha. The same principle applies. The expansion of cosine pi minus alpha is denoted as cosine pi, cosine alpha plus sine pi, sine alpha. The input value is calculated as negative cosine alpha. We successfully proved these two questions. So what is the relationship between the two induction formulas above and the cosine formula of the difference angle? In fact, both of these formulas can be expanded and organized using the cosine formula of the difference angle to prove. The cosine formula for the difference angle is a generalized extension of two induction formulas, and these two induction formulas are actually regarded as special cases of the cosine formula of the difference angle. This is what we call the special and general relationship. Let's take another look at example 2. Sine alpha is equal to 4/5. Alpha belongs to the range of half pi to pi. Cosine beta is equal to 5/13 of the negative value, where beta is the third quadrant angle. Calculate cosine alpha minus beta. The cosine formula for the difference angle requires cosine alpha minus beta, so we need to know the sine and cosine values of alpha and beta. The title has already given sine alpha and cosine beta, but missing cosine alpha and sine beta. Then we need to use the sum of squares of the same angle here. Before use, we must pay attention to the quadrant where the angle is located in order to determine the positive or negative values of the trigonometric function. We can solve it this way. Sine alpha is equal to 4/5, and alpha belongs to half pi to pi. We can get that cosine alpha is equal to the negative root of 1 minus sine square alpha, and its value is negative 3/5, because cosine beta is equal to negative 5/13. Beta is in the third quadrant. So we can see that sine beta is a negative angle. So minus cosine beta, which is equal to the negative root sine, is equal to negative 12/13. Substitute it into the formula, multiply by the same name, add symbols, and its value is negative 33/65. This question still emphasizes the application of the square-sum relationship of the same angle, and we must pay attention to the quadrant where the angle is located. Let's recall what we talked about in this lesson. In this lesson, we have mastered the cosine formula of difference angle and understood its derivation process. So, in the process of derivation, in order to illustrate the arbitrariness of alpha and beta, we used classification discussion. Then, in order to prove the form of the formula, we introduced the definition of trigonometric function, that is, the combination of number and shape. In order to illustrate the relationship between the difference angle cosine formula and our induction formula, we have experienced the special and general. That's all for this class. Goodbye.